Okay, today what we're going to do are indirect truth tables. But before we do that, we have to do some preliminary knowledge, right? You need to be able to deduce the truth values of statements given the truth value of some main operator. So what do I mean? Let's say we had A and B, and this was true. What are the truth values of A and B? Well, it has to be the case that they're both true, right? Because if either one of them were false, then the main operator would be false. So we deduce that B is true and A is true. Likewise, if we had the statement A then B, and this was false, we know that that only happens when A is true and B is false. So that must be the case. That must be what their truth values are. But what if we had a case where we have A then B, and our horseshoe is true? We can't actually deduce the values of A and B because we don't have enough information. There are three possibilities for what A and B could be. We could have true, true, false, true, or false, false, right? But what if we were given B? Say B, we were told, is false in this situation. Well, now A can only be true or false. But if A is true and B is false, then the main operator should be false. And that's not the case. We're given that the main operator is true. So it must be the case that A is false. So that's the kind of deductive skills you need to have to be able to do some of these more complicated indirect truth tables. So now let's actually show how to complete an indirect truth table. So let's say my premises, right, for some argument are not A, then B or C. Now remember, we're going to separate premises with a single diagonal. I have not B as another premise, and then we separate our premises from our conclusion with a double diagonal. And our conclusion will be C, then A. Now, for an ordinary truth table, we have three variables here, so this would have 8 rows. Because if we have n variables, we have 2 to the n rows. And so I don't want to make a truth table that has 8 rows. That's a lot. For an indirect truth table, this will only take 1. And what we do for an indirect truth table, we want to show that our argument is invalid. These are tests for invalidity. When is an inference, an argument invalid? It's invalid when the premises are true and the conclusion is false, right? So what we do is we assume that the premises are true. So we have to locate the main operators. So not is going to be true. Oh, sorry, that's the horseshoe is true. Not will be true. And then this main operator, the horseshoe, will be false. So we assume that the premises are true and the conclusion is false. Now what we do, using those deductive skills that we just went over, is we deduce the truth values of all of our statements, right? So starting with not, right? We have not B. Okay, well, it must be the case then that B was false, right? Okay, and so if we know that B is false, there you go. We'll just fill that in right there. I'm looking at my conclusion right now, and I see that the horseshoe is false, so it must be the case that we have true then false. Okay, so that gives us all of our statement values. We have C is true and A is false, which means not A is true. And now what we want to do is we want to look for any contradictions. Every single truth value of our statements were forced in this situation, right? So we want to see if, by assuming the premises were true and the conclusion was false, if we somehow got a contradiction. What do I mean by that? Okay, well, not B is obviously not a contradiction. It's just a truth value. We have false for that, right? C then A, we said is false. C is true, A is false. That all lines up. A then B or C, right? We have that is true. Well, B or C is going to be a true statement since B is false and C is true. And then not A we said is true, so we have true then true. And that all works out. That means that our horseshoe should also be true. So there we go. We didn't reach a contradiction. So since we did not get a contradiction, and we assume that the premises are true and the conclusion was false, and we didn't get a contradiction, then this is an invalid argument. What this shows us is that it is possible, under some assignment of values for our truth values, for our statements, in this case, if we assign A to be false, B to be false and C to be false, we end up with a situation where the premises are true and the conclusion is false, and that's an invalid argument. So by doing this indirect truth table, we have shown that this argument is invalid. Now we have two more examples, and you want to stick around for both of them because they're going to highlight some important cases that we might run into. Okay, so our next premise is A then B or C. Our next premise is B then D. Our next premise will be A. And then our conclusion will be not C then D. So as you can see, this has 4 variables. The truth table would take up 16 rows. This will take up less. All right, now let's make our premises true and our conclusion false. So we have this is true, true. Oh, sorry. This should not be true. That's not a premise. This is true and this is false. Okay. Well, how can we force some variables? Well, we have our implication, our horseshoe at the end is false, right? So it must be that not C is true and D is false. So that means that C is false. And so now let's fill that in elsewhere, false and false. Okay, I'm looking at the second premise, B then D. That horseshoe is true and D is false, so it must be the case that B is false. Okay, then we can write that over here, that B is false, and we know that A is true. Okay, so no contradiction so far. False then false is true, A is true, true then false is false. Now let's look at our first premise. Okay, so B or C, false or false, that is false. Oh, and then here's a contradiction. So we said that A is true and B or C is false. And then we said that A then B or C is true. That's not true, right? We said that true then false is true. That's a contradiction, right? This should be false. So, and we got this contradiction by assuming that our premises were true and the conclusion was false. And in doing that, every single truth value assignment for our statements was forced, right? We never just arbitrarily chose them. It was forced by the truth values of our main operators. And so by assuming that the premises were true and the conclusion was false, we actually hit a contradiction. So what this contradiction shows us is that it can never be the case that the premises will be true and the conclusion is false. So in this case, our argument is actually valid. Remember, with the indirect truth tables, we're trying to show that the argument is invalid. So if we hit a contradiction, it would show that the argument is valid. But not all the time will it be nice and work out like this. Not all the time will our statements be forced. Sometimes we have to go through multiple cases, but it'll still be less than doing an entire truth table. So let's look at one of those cases. What if I had the premises, let's say, not A, then B? I'm trying to write bigger so our truth table doesn't look so muddy. And then let's say we had B, then A. One more premise, let's say we had A, then not B. And then what if our conclusion was A and not B? Well, we're going to do this like we do with all of them. We're going to assume that our premises are true, and our conclusion is false. Now, in this situation, nothing is forced, right? There are 3 ways our implications could be true, and 3 ways that our conjunction can be false, right? So, what we're going to have to do is have 3 rows for our 3 rows for our indirect truth table. What we want to do basically is complete all these rows. So here, how many ways can A and not B be false? That's 3 ways. Where we have, let's say, true and false, false and true, false and false. So there you go, false, false. And then from this, we get that B is true, false, true. Now what we want to do is fill out the indirect truth table as we have been on each row. And On each row, we are trying to avoid a contradiction. Remember, we're trying to show that these arguments are invalid, right? And the only way to do that is by assuming that the premises are true, the conclusion is false, and not getting a contradiction. On any row, if we do not get a contradiction, we will have shown that the argument is invalid. If we do get a contradiction, let's say we get a contradiction on the first row, what we need to do is keep going and completing the truth table, right? The argument will be valid if every row is a contradiction, invalid if even one row does not have a contradiction. So let's fill out this truth table and see what I'm talking about. Okay, so on the first row, A is true and B is true. So let's just assign truth values everywhere and start filling them out. So not A is false, so we get false then true is true, so that works. We on the second premise, true then true is true, that works. Third row, we have true then false. That is a contradiction. We said that true then false is true. All right, we got a contradiction. But again, if we get a contradiction, we need to keep going because what we're trying ultimately to find is a case where there is no contradiction. Okay, so let's keep going. On the second row, we have A and B are both false, I think is the case. Oh, it looks like, hold on, it looks like I messed up one of these down here. Yeah, I messed this up. Okay, let's fix that. So for our second row, A and B are both false. So let's assign that. We have false, false. Oh, and let's just show that our premises will always be true. There you go. Premises are true. A and B are both false. Let's finish this out. False, false. Okay, so with our first premise, A will be, not A is true, and we have true then false is true, and that's immediately a contradiction. All right, we got a contradiction in our second row. We don't even have to fill out the rest of the second row. It doesn't matter. We already had a contradiction. I don't care if we have double contradictions. Now we're going to go to our third row and hope. So we want it to be invalid for some reason, and hope that we don't get a contradiction. So in this row, A is false while B is true. So A is false, B is true, B is true, A is false, B is true. All right, starting with the first premises. So we got not A is true. So the whole statement true then true is true. Okay, that works. Second premise, true then false is true. Immediately, contradiction. All right, so now what do we do in this case? In this case, we have covered all of our cases for when the premises are true and the conclusion is false. And in every case, we contradicted ourselves, meaning that assuming that the premises are true and the conclusion is false doesn't work out, that there's no truth value assignment to our statements that could ever yield a case where the premises are true and the conclusion is false. We got a contradiction in every case, which means that the original argument, all my premises and my conclusion, that argument is valid. If at any point we were doing this, right, and on the first row there wasn't a contradiction, you just stop right there and say that the argument is invalid. If we had the worst case scenario where we have, I don't know, let's say 4 variables, or no, okay, that's a little crazy. But let's say we had another situation where we had to cover like 4 cases, and the first 3 were contradictions, and then the last one wasn't. Well, I mean, you're going to stop regardless because you just filled out the entire truth table. But since you didn't hit a contradiction on that last line, the argument is invalid. So the key takeaway here is that if you get a contradiction in a single case, you stop immediately, the argument is invalid. If you get a contradiction, you got to keep going, and if it turns out that every case leads to a contradiction, then the argument was valid in the first place. So that's all for this video. If you made it to the end of this video, thank you for sticking it out. I know that this was a difficult one, so I appreciate it, and I hope you learned something.